In this video, the fundamental frequency of the sound that different instruments produce will always be the independent variable. Since this video is going to explore the different factors that affect an instrument's natural frequencies, the dependent variable will change in each experiment. As you will soon learn, the natural frequencies of instruments are comprised of harmonics with the lowest frequency being the fundamental frequency. Thus, any factor that affects an instrument's natural frequencies will affect both its fundamental frequencies and harmonics. Because an instrument's fundamental frequencies are the easiest to hear, this video is going to focus on those specific frequencies. A key principle to remember while doing these experiments is that humans interpret low frequencies as low pitches and high frequencies as high pitches. For me, formulas are helpful tools in understanding science concepts since they serve as guides to thinking, highlighting the relationships, direct or inverse, between variables. It's for this reason that before we get into the three experiments, we're going to derive a formula. To make sure we do not become confused about which variables represent what quantities, all the variables are given in the upper right-hand corner of the screen. This derivation is going to be simple because we are only going to use two formulas. The two formulas we are going to use is F1 equals V over 2L and V equals the square root of T over M, where F1 represents the instrument's fundamental frequency, V represents the speed of sound waves produced by the instrument, L represents the length of the string, T represents the tension of the string, and M represents the mass of the instrument. Since both formulas contain a variable which represents the speed of sound waves produced by the instruments, I can substitute the formula, the square root of T over M, for V into the formula F1 equals V over 2L, attaining the formula F1 equals the square root of T over M over 2L. Once I simplify the formula by distributing the radical between the fractions and flipping the denominator, we attain the formula F1 equals the square root of T over 2 times L times the square root of M. There are many pieces of information this formula elucidates. It makes clear that as the length of an instrument string increases and mass increases, the magnitude of its frequency decreases. In this next experiment, we are going to test how the length of a string represented by the letter L in the formula affects the fundamental frequency of an instrument called a zither. Of course, the zither we will be using is very simple. It is a plank of wood as its base, with two screw rods attached and a string tied in between each of them. To test how changing the length of the string affects the zither's fundamental frequency, I'm going to hold one end down with a pencil, changing the length of the string or furling it. Because only the part of the string between the screw and the pencil will vibrate when it's drawn by my finger, this part of the string will be considered the instrument's length in any given instance. Looking at the formula for fundamental frequency, which we derived earlier, F1 equals the square root of T over 2L times the square root of M, we can explain why these results make sense. According to the formula, as the length of the string between the pencil and the screw increases, its fundamental frequency decreases, meaning its pitch got lower. Our observations align with this concept because as I move the pencil away from the first screw to a point near the first screw, the middle of the string, at a point near the second string, the pitch got lower, meaning that the instrument's fundamental frequency decreased. In this last experiment, we will be exploring how the mass of an idiophone affects its fundamental frequency. All our other instruments, the idiophone used in this experiment will be very simple. All that it consists of are glasses with varying volumes of water. The first glass is completely full, the second glass is 2/3 full, and the third glass is 1/3 full. In order to make the glasses vibrate so that they produce sound, I will rub my wet finger above their rims. Even though an idiophone is a percussion instrument as opposed to a string instrument, this experiment still illustrates how the mass of an instrument affects its fundamental frequency because mass affects the fundamental frequencies of string instruments the same way that it affects the fundamental frequencies of percussion instruments. Let's try out our prediction. Let's see how our results match up with the information given by the formula. Because in the formula, F1 equals the square root of T over 2L times the square root of M, mass, which is represented by the letter M, is under the bar, it's clear that mass is inversely proportional to the fundamental frequency, meaning that we can predict that as the quantity of water in the mass of the iodophons increases, the fundamental frequency of the instrument will decrease and the pitch it produces will get lower. That's exactly what happened. Just as the formula states, the glasses with higher masses have lesser pitches, meaning that their fundamental frequencies are small, while the glasses with smaller masses have higher pitches, meaning that their fundamental frequencies are larger.